This is the story of a Victorian railway bridge.
I am standing on the old towpath by the River Wear at Durham City, looking across towards the cathedral and castle. Here, upstream of the city, is the racecourse on which the miners' gala big meeting has been held since Victorian times. And each June the regatta takes place along this stretch of river.
Walking further upstream, we round a bend and come across this sturdy brick structure. It is a ruined and overgrown abutment which once supported an iron railway bridge across the river. The matching abutment on the other bank is also still here, though its arch has collapsed. Two old photographs of the bridge, which span the river here, show what a fine, picturesque structure it was. We are grateful to Durham historian Michael Richardson for these rare photos.
The bridge was built in 1892 to carry the North Eastern Railway Company's line from Sunderland directly into Durham. This was a partial rerouting of the existing line, which passed through the colliery villages of Ryhope, Merton, Hetton, Pittington and Sherburn. The 1892 extension ended at a new railway station in the Elvet district of Durham, just behind the racecourse. The project involved building this iron bridge, a brick arch over Old Durham Beck, and a mile and a half of new track from the tiny Sherburn House station. The line replaced an earlier one which had ended at Shincliffe village.
In this modern aerial view, we are looking along the remains of the embankment towards Elvet. The total cost of the line extension was over £30,000, of which about £4,500 was spent on the iron bridge, about £500,000 in today's money. Elvet Station opened in 1893. However, the venture was not a commercial success. It closed to passengers as early as 1931 and to freight in 1954. The exception was once every July when special excursion trains brought miners and their families to the big meeting on the racecourse.
The bridge was demolished in 1963. From my school at the top of Winnie Hill, I watched the flames of the oxyacetylene cutters as men took down the ironwork.
In this video, we will use computer graphics to show how this impressive bridge may have been constructed and what it looked like. We are most grateful to the North Eastern Railway Association for finding in their archive the original engineering drawings. The designer was Charles Harrison. The concept is simple. The railway tracks ran on a deck supported by two girders between the top of the abutments and supported below by arched girders which butt against the brickwork at a lower level. Criss-cross spars stabilise and stiffen the structure. The span was 130 feet, about 40 metres. The finite element simulation illustrates, on a grossly exaggerated scale, how the bridge would deform under the moving load of a train.
The drawings formed part of the contract with Thomas Ridley of Middlesbrough to build the station, the bridge and the new stretch of line. The ironwork was subcontracted to the Stockton Forge Company. We can only speculate how the bridge and station were built. It seems likely that the embankment from Sherburn House was first, so that the workmen, building materials, iron sections and steam-driven machinery could be brought in from Middlesbrough, Stockton and Sunderland. Other bricks, lime, scaffolding and wooden planks may have been hauled by horse and cart, or floated upriver on a barge towed by horses. Construction was by hard manual labour. Thomas Ridley had 300 men working on the project. In the computer graphics which follow, we give some impression of how work may have proceeded week by week. Therefore, in the spirit of a model railway, here is the section of riverbank on the east side. The river level is about 10 feet below the road. That's about 3 metres.
After the land had been surveyed and the vegetation cleared away, the men started digging. They may have been helped by steam-powered mechanical diggers. The soil and stones were probably moved to build up the embankment.
A support of wooden cribbing was erected around the walls of the deepest hole beside the river. Water seeped continuously into this muddy pit, since its bottom is lower than the river bed. So while some men were digging, and others hauling the spoil to the surface, yet others were pumping out the water or bailing it in buckets.
The foundations, like the whole abutment, are in 3 parts. First, a 12 feet deep block of concrete under the massive riverside tower, which supports the ironwork. Second, there are 6 feet deep blocks under the road arch.
And third are inclined blocks of concrete under each of the wing walls. In this cutaway we can see these concrete foundations.
Concrete is an aggregate of sand and gravel, bonded by a cement powder which sets hard when water is added to the mix. There had long been a need for water-resistant cements, and Portland cement had been invented in 1820 to meet this need. It sets by chemical reaction with the water and becomes hard in a day or so.
By 1890, concrete made with such a quick-setting, water-resistant cement was the material of choice for foundations, particularly on a riverbank.
Once the concrete had set, a massive block of bricks in cement was built on top of this deepest concrete block. It is 12 feet wide and 22 feet long.
The drawing specifies bricks in cement to be used here. This means that the mortar should contain Portland or similar cement to make it water resistant should the river level rise high.
The wooden cribbing was sawn off and the excavations widened to allow the bricklayers more room to work. The men also laid a terraced brick base around the other concrete foundations.
The positions where the arched iron girders press against the brick abutments is called the springing. The end of each girder fitted into a cast iron plate which was bolted to a massive granite block cut at an angle of 23 degrees. These blocks were set into a solid pyramid of bricks in cement. Today, when the river level is low, you can still see the concrete foundations supporting the block of bricks, and its tapered pyramid above. One iron plate is also still in place.
The higher brickwork in the riverside tower and elsewhere would have been constructed in the traditional way with interlocking courses of bricks in a lime mortar. This mortar would have been mixed in troughs on site by pouring water onto quicklime. It hardens very slowly through chemical reaction with carbon dioxide in the air. Under the roadway they built an inverted brick arch, mirroring the arch over the tunnel. This would prevent the walls of the tunnel from creeping inwards under the weight of the trains. The wing walls, which held back the embankment, were 6 feet thick at their base. They were tapered in height and along their length, and each had a pillar at the end. Nothing of these pillars can be seen today.
Once the brickwork was above road level, the trench was filled in. There are hidden internal structures. There are 2 arched chambers inside the main tower and a single arch next to the embankment. These would be strong enough to support the moving loads above. Apart from the internal arched chambers, the whole abutment appears to be solid brickwork. There is no indication of rubble infill between walls, which had long been a common practice. Towards the top of the main tower, 2 large padstones were placed directly above the granite blocks to bear the girders of the bridge deck. A curved wooden former would have been used as temporary support while the bricklayers built the arch. The tunnel is 17 feet long, 12 feet wide and 12 feet above the roadway.
The architect made the abutment pleasing to the eye by adding a stone cornice. Similar stones capped the wing walls. On top are the parapets, though they were not completed until the upper girders were in place. The rails on wooden sleepers ran centrally between them. The west abutment and the 2 embankments would have been finished at about the same time. If we imagine all the soil removed, the full size of the abutment is plain.
While the abutments and embankments were being completed, the iron girders were being forged in Stockton and preparations made on the river to erect them.
The total weight of the iron was reported as 130 tons. However, there was a limit of perhaps 10 tons to the single weight which could be raised into place, so the largest girders were fabricated in sections and joined together on site.
The bridge was made of wrought iron plates and angles fastened by rivets. This contrasts with the welded steel structures of today. Wrought iron was traditionally made from impure pig iron in a dish-shaped hearth furnace heated from above by hot gases from burning coal. The molten iron was stirred with long iron rods by burly sweating men. Added oxides and hot gases from the coal combined chemically with impurities in the iron to form a slag, so refining the iron. Most slag floated to the top and was skimmed off, but many small particles remained trapped within the melt.
The iron was ready when it stuck together in pasty lumps. When lifted from the furnace, each orange hot lump was forged into a crude block using steam-powered hammers, which squeezed out more of the slag. Several blocks were then forged together and squeezed again. Rivets and other small items were made by forging them to shape, whilst plates, bars, angled sections and rails were made in a rolling mill. The repeated forging and rolling elongated the entrapped slag particles to give the iron a fibrous texture resembling wood.
Riveting was used to make iron ships as well as steam boilers and bridge girders. It was a way of stitching two flat iron sections together. Matching holes were drilled in each section. The flat sections were then overlapped and temporarily secured in position with nuts and bolts. A red-hot rivet was taken from the furnace and quickly pushed through one pair of aligned holes. A tool with a dish-shaped recess was used to hold the mushroom head firmly against the plate, whilst a similar tool hammered the protruding rod, deforming the softened iron into a second mushroom head. As the rivet cooled, it contracted and pulled the plates tightly together.
In the factory, rivets could be fitted quickly by one operator using a hydraulic press, but on site 2 men were needed, one to hold the rivet head, while his workmate hammered the protruding shank. Most of the bridge was made by riveting 1/2-inch thick plate and 4-inch L-shaped angle sections together. The largest girders were box-like and hollow to allow access to both ends of each rivet. Plates and sub-assemblies were joined by butting them together and adding 1 or 2 cover plates.
A weight-bearing beam typically has 2 horizontal flanges joined by a vertical web. The beam gains its stiffness from the fact that, as it bends under the load, the top flange must contract, while the lower one must expand. The wider the separation of the flanges, the larger the effect. In fact, doubling the web height produces an 8-fold increase in stiffness.
These pictures illustrate the designs of the large arched girders and the smaller straight deck girders. The arched girder, called a rib, is 28 inches wide and its lower section is 36 inches high. On top are extra inner and outer webs to which the criss-cross bracing is fastened. Similarly, the deck girder has a single 14-inch high channel beam added on its outer side.
Here are full sections of a rib lying on the factory floor awaiting transport to site. Note how the upper webs are offset with respect to the main body of each section. Each section was 16 feet long and weighed 2 1/4 tons. We have not shown the many holes drilled for more rivets to be added on site. The girder ends are reinforced, especially the end which presses against the iron plate on the abutment.
The two deck girders just rested on the abutments. They were not solidly built in. Similarly, the arched girders simply rested on the iron end plates, angled at 23 degrees. These flexible joints allowed the girders to expand and contract as the temperature changed from summer to winter. However, it also meant that each girder section had to be individually supported until all of its sections had been fixed together. Only then would the whole girder become self-supporting.
The site engineer was Mr. William Mead King. By careful logistical planning, he and his colleagues determined the best order in which to bring the sections to site and how to erect them into place. We will now conjecture one way in which this could have been done. We do know that a wooden bridge had been built across the river in the summer of 1892, because newspapers reported that it was bodily swept away by floods that October. So a replacement wooden platform had to be built on stout trestles driven into the riverbed. This would have been started while the bricklayers were still building the abutments.
We suppose that Thomas Ridley's men used a steam-powered crane mounted on a railway truck. This could lift the iron sections from a wagon onto the wooden platform. We further suppose that no similar crane could be brought to the Elvet side, but instead a steam traction engine pulled the ropes and cables. Flat trolleys on narrow rails could then carry the sections across the river. Starting at the Elvet side, sections of the two ribs were manipulated into place one by one, using ropes and pulleys, and propped up on sturdy wooden frames. Their precise heights would be adjusted with hydraulic rams and wedges before they were temporarily bolted together. Some cross-bracing was also bolted on to add stability and fix their spacing. Once all sections were bolted together using cover plates and bracing bars, the structure would be self-supporting and capable of bearing modest loads. The trolley rails would be removed from under each completed section in turn.
In order to erect the upper deck girders, we suppose that a higher platform was built, supported on horizontal beams. Near the abutments, these could be held aloft on vertical posts positioned along the edges of the low platform. Towards the crown of the bridge, however, the geometry required that the posts stand between the ribs. If we hide the ribs and their supporting frames, we can see this forest of wooden supports more clearly.
In our scenario, the two narrow trolley rails were relocated onto the higher platform. A hand-operated crane was unloaded from a railway wagon and placed to straddle two trolleys side by side. The crane operator lifted sections of the upper girders from a third trolley and lowered them into place. Each section weighed 1¼ tons. These would be temporarily bolted together with cover plates and braced by several L-section bars to the ribs below, criss-crossing the triangular space called the spandrel. The teams of riveters probably started by riveting together the cover plates which join the sections of ribs. This would strengthen the ribs before all the upper girders were in place to ensure that they could take the increasing weight from above. However, it is unlikely that the upper girders were rigidly riveted until Mr. Meade King had carried out a thorough check on position and alignment. The riveters would have had to have blacksmiths' forges to heat the rivets close to where they were working.
The hand-operated crane would also be used to lift the transoms into place. These are the beams between the upper girders which form the deck. Each is 14 feet 6 inches long and weighs about 3/4 ton. Short sections of the trolley rails would be removed in turn to allow 2 or 3 transoms to be fitted at a time, 5 feet apart. The parapets of the abutments could now be completed and the railings added. To these the designer added decorative bosses. We leave you to imagine the dozens of men, the ladders and extra scaffolding during this hive of activity. The deck on top of the transoms consisted simply of strips of iron. Looking down between them, you would have been able to see the river. The mountings for the rails were squared off wooden logs bolted into iron channels. The criss-cross bracing across the spandrel and underneath the ribs could not be completed until the vertical posts supporting the upper platform were removed.
All the ironwork would be painted to limit rusting, since corroding wrought iron can split apart along the slag inclusions. The relatively recent photograph from Michael Richardson shows it dark grey. Here we have imagined it newly painted in dark green, with the bosses on the railings picked out in bright green, the North Eastern Railway Company's livery colour.
At last the scaffolding and platforms were taken down, the rails were laid and the line completed into Elvet station. Before the line could go into service, a full engineering safety assessment was legally required. This was conducted by Major General Hutchinson of the Royal Engineers on behalf of the Board of Trade. He measured the deflection of the bridge when a train moved to the middle and pronounced it satisfactorily small, no doubt to the relief of Charles Harrison the designer, William Mead King the site engineer, and Thomas Ridley the principal contractor. As one newspaper put it, skill triumphed over any difficulties.
The Mayor and Corporation of Durham City wanted a grand opening ceremony with bunting and speeches, but the North Eastern Railway Company were content just to sell the first ticket. And so the Durham Elvet to Sunderland line opened on the 24th of July 1893, ready for that year's Miners' Gala.
Though only a single track had been laid, the railway company hoped for such large numbers of passengers that they had made provision for a second track by buying enough land to widen the embankment if needed. The bridge, however, could not accommodate a second track. In the event, there were relatively few rail users, and so the line closed to passengers after Christmas 1930.
In addition to the Miners' Gala excursions every July, we note the Summer's Day in 1911 when Lord and Lady Londonderry, the vastly wealthy land and coal owners, invited 3,000 children from schools around Durham City to a jamboree garden party at Seaham Hall, their country estate. The children travelled on 4 special trains from Elvet Station. The event was to mark both the coronation of King George V and of Lord Londonderry himself becoming Mayor of Durham.
The party included 101 scholars and 7 teachers from Gilesgate Infant School, a school which I later attended. The Durham Chronicle newspaper reported that the children were in excellent spirits, all looking forward to a delightful outing by the seaside. After tea, the children were marshalled to sing the national anthem and be addressed by his lordship. Each child then received a commemorative medal bearing the profiles of the Marquess and Marchioness.
The event epitomised the social structure and the communal values of that time.
When I was a boy, my father took me in a rowing boat from Brown's Boathouse in Durham almost as far as Shincliffe. Everything looked different from the river. The bridge seemed immense and eerie as we passed under its strange canopy of criss-crossed iron bars.
With that reflection, we close our story and leave the bridge, Elvet Station, and the railway line through the pit villages to fade into history.